Hello everyone, welcome to this video lecture of this course finite element method. So in the earlier lectures we have studied the concept of this finite element method, then its origin, that is the historical background of this finite element method, what is the discretization or dividing a complex domain into various subdomains, then what is the concept of the element, then node or nodal points. All these things have been studied earlier. Then there are different steps to this finite element method and different phases like the pre-processing, processing, that is the solution or solver, and the post-processing part. So all these things have been discussed earlier regarding this finite element analysis. So in this lecture we will study the weighted residual method. It is one of the most important method of this finite element analysis. So how to solve different numericals based on this weighted residual method, that will be discussed in this lecture. So let us start this lecture. So earlier, while discussing the concept of the finite element analysis, we have seen that a designer or an analyst, he needs certain requirements to design and assemble the parts of a product. So that means there will be some requirements, and those requirements are like the displacement at certain points of the product, and maybe the stress distribution or the natural frequencies, then different vibration or the pressure, velocity or temperature distribution or fatigue life. So all these things are some requirement to design and to assemble a product. Now, to fulfill that requirement, there should be different method for engineering analysis. Now, what are those methods for using which the requirements for an designer or an analyst can be fulfilled? And there are actually three different approaches or the method for engineering analysis. One is the experimental method, another is the analytical method, and number three is the numerical method or approximate method. And we know that finite element method, it is a numerical technique or numerical method to find the approximate solution of partial differential equation. So what are these three different methods of engineering analysis actually? Number one is the experimental method. So in this experimental method, actually we use the prototype. Now if we want to change the dimension of that prototype, we have to actually disassemble the entire prototype and again reassemble it, and then the testing will be carried out. So this type of experimental method or experimental analysis, it needs manpower and material. So that means it is actually time consuming and costly also. So in this experimental method, this is actually very much costly and time consuming, which needs the manpower and materials, because if there is certain change in the dimension or the size or the shape or maybe anything of this prototype, if you want to change that part, then we need to disassemble the total prototype, or maybe some part of that prototype, again we need to reassemble it. So again we need to carry that experimental analysis or the testing to gain the accurate result. So that means it is very much very much time consuming and costly also. So next we are having the analytical method. So what we need to do in this analytical method, here some problems, these are expressed by mathematical differential equation. So it gives actually quick and closed form solutions, and it is used only for the simple geometries and idealized supports and the loading conditions. So some analytical method we will discuss today. So some mathematical differential equation will be there, and those mathematical equations we need to solve based on the different methods. So today we will discuss the point collocation, then subdomain collocation, least square method, and the Galerkin method. All these different methods we will discuss today, taking an example of a mathematical modeling or a problem. Next we are having the numerical method. Now what we know that the analytical solution, it can be obtained only for certain simplified simulation or situation. So when there will be some complex problem which involves some complex material properties or some boundary conditions, then actually the designer or the engineer, they prefer the numerical method that gives approximate but acceptable solution. So this is the concept of the numerical method. There we will get some approximate but acceptable solution, but it is applicable for the complex situation where we will put some material properties and boundary condition to the computational domain. Now in this numerical method we are having various method like finite difference, then finite volume, then finite element. So this finite element method, it is one type of the numerical method. So in this finite element method, what we do, it is actually a numerical method which is used for solving problems of engineering and mathematical physics. Okay, so what we do there in this finite element method, that a body or a complex structure, it is which we need to do the analysis part. It is actually subdivided, that complex shape of the body, it is actually subdivided, which is also known as the discretization. So it is actually subdivided into the smaller elements of finite dimension. So that's why the name of this method is finite element. Now then, after subdividing the total complex shape into smaller components, the body is considered as an assemblage of these elements which are actually connected to each other and at a finite number of joints which are known as the nodes or nodal joints. So the elements of that complex shape of the body, these are actually connected by the nodes or the nodal points. Now the properties of each type of the finite element, it is obtained by the simulation, and they are assembled together and solved as a whole to get the solution of the total or whole complex shape or the complex structure. Okay. Or that means what we do in case of this finite element method, that means instead of solving the problem for the entire complex shape in one go or in one operation, we actually formulate the equation for each finite element and combine them to obtain the solution of the whole body. Okay? So this is the main concept of this finite element method. So we don't go to solve the entire complex shapes problem. We actually do the discretization. That means we actually subdivide that entire shape into some smaller elements which are actually connected by the nodes or nodal joints. After that, we formulate the equation for each and every finite element, that is that small elements that has been subdivided. So we formulate the equation for each and every finite element or smaller element, and then we combine them to obtain the solution of the whole body or the whole structure. So that means this finite element method, it is actually used to solve the physical problems which involves some complicated geometries, or there may be some loading or the material properties which actually cannot be solved or pretty complex to solve by the analytical method. Okay, so this is the main concept of this finite element method, And for this analytical shape, we have seen that we go for the simpler structure, and in case of finite element method we use those finite element method for the complex shape or the complex geometries. Now, one of these analytical method, it is the Galerkin method. Now, what is this Galerkin method? This Galerkin method, it actually incorporates differential equations in their weak form. That is, before starting integration by parts, it is in strong form, and after by parts it will be in weak form, so that they are satisfied over a domain in an integral. That means in case of this Galerkin method, the equations are satisfied over a domain in an integral or average sense rather than at every point. So this is the concept of this Galerkin method or weighted residual method. Let us discuss one numerical based on this weighted residual method. So what is given in this question? The following differential equation is available for a physical phenomena ae d2y dx2 plus q naught equals to 0 with a boundary condition at y 0 equals to 0, x equals to L, or dy dx equals to 0. Now we need to find the value of fx using the weighted residual method. Okay, so this is the question given here, and the boundary conditions which are given at x equals to 0, y equals to 0, but at x equals to capital L, dy dx, this is equals to 0. Now we need to find the value of fx using the weighted residual method. So how to proceed in this numerical? First, we need to take into assumption a trial function or trial solution. So that trial function, it is a polynomial. So that means the yx, this is equals to a0 plus a1x plus a2x square. This is the simple polynomial trial solution. In this case, yx equals to a0 plus a1x plus a2x square. So this is our equation number 1. Now if we apply the boundary condition, so here we are having two boundary conditions. First one is written y 0 equals to 0. So this boundary condition means at x equals to 0, y equals to 0. Now let us put this first boundary condition in the trial function, that is yx equals to a0 plus a1x plus a2x square. Now if we put x equals to 0 at y equals to 0, in that case yx, this is 0, then a0, this is a constant part, then a1x. Now here x will be equals to 0, that means this a1x, this is also 0. Next a2x square. So as x equals to 0, so this x square is 0, and this last part of this equation a2x square, this is equals to 0. So that means putting the first boundary condition, that y equals to 0 at x equals to 0, putting this boundary condition, we are getting a0 equals to 0 from this trial solution. Now if we put the second boundary condition, that means x equals to L at dy dx equals to 0. So if we put this boundary condition in the second boundary condition, that means first we need to do the first order differentiation of this trial solution. Now yx equals to a0 plus a1x plus a2x square. Now if we do the differentiation, first order differentiation, that is dy dx. So in that case, as a not equals is a constant, so the differentiation, this is 0. Then in case of a1x, the first order differentiation, it is only a1. And in case of a2x square, in this case a2 is constant, and ddx of x square, this is actually 2x. So that means that dy dx, this is equals to a1 plus 2a2x. Now in this equation, if we put the second boundary condition, that is at x equals to L, dy dx equals to 0. That means the left hand side of this equation, this is 0, and in the right hand side, if we put x equals to L, then we are getting the right hand side as a1 plus 2a2L. So that means from this equation we are getting the value of a1, this is equals to minus 2a2L. Okay, now we need to find the value of the a2 from that polynomial equation. We have already calculated the value of a0, this is equals to 0, and the value of a1, this is equals to minus 2a2L. Now if we put these values of a0 and a1 in the equation number 1, then we are getting yx equals to a0 is 0, a1 is minus 2a2L. Now it was a1x, so it will be minus 2a2xl plus a2x square. So that means yx equals to a2 within bracket x square minus 2xl. So this is our equation number 2. Now if we do the first order differentiation of this second number equation, then we are getting dy dx, this is equals to a2 is a constant part, then ddx of x square, this is 2x, and ddx of 2xl, it is only 2l. So that means dy dx, this is equals to a2 into 2x minus 2l. Now if we do the second order differentiation of this equation, then we are getting d2y dx2, this is equals to 2a2 only, because the other part, that is 2a2l, this is a constant with respect to x. So we are having the second order differentiation of y with respect to x, this is only 2a2. Now what it is given here, that ae d2y dx2 plus q naught equals to 0. So that means the residual r, this is equals to ae d2y dx2 plus q naught, this is equals to 0. Now in this equation we have found the value of d2y dx2, which is actually 2a2. So if we put this value here, so we are getting ae 2a2, this is equals to minus q naught. So from this equation we can easily find the value of a2, which we are getting as minus q naught divided by 2ae. Now if we put this value of a2 in equation number 2, then we are getting the value of fx, that is y, this is equals to minus q naught by 2ae within bracket x square minus 2xl. So this is the value of the y or fx, which we have calculated using the weighted residual method. Okay, so what we have done here, we have taken into consideration one polynomial function, which is a0 plus a1x plus a2x square. After that, we have entered the two different boundary conditions which are given here. That is the first boundary condition, it was y equals to 0 at x equals to 0, and the second boundary condition, it was dy dx equals to 0 at x equals to L. Now putting these two different boundary conditions, we have calculated the value of a0, a1, these two things. So we have got that a0 equals to 0, and putting the second boundary condition, we have found the value of a1, this is equals to minus 2a2L. Now after putting this value of a0 and a1 in the main polynomial function, we have got one expression of yx. So here we have done the second order differentiation. That means we have found the value of d2 by dx2. So that value of d2 by dx2 we need to put in the equation of the residual. So the mathematical representation of the residual, that is ae d2 by dx2 plus q naught equals to 0. It was given that formulation. So that means in this equation d2 by dx2 we have entered the value of d2 by dx2, that is we got as 2a2. Now putting this value, we have calculated the value of a2 also in the form of q and ae. Now finally we have entered that value of a2 in the equation number 2, by which we have calculated the value of y or fx using the weighted residual method. So this is the procedure to solve such numerical using this weighted residual method. Let us discuss the second numerical. What it says, that find the solution for the following differential equation: d2 by dx2 plus 50, this is equals to 0, and the value of x, it is within 0 to 10. The trial function, it is given y equals to a1x multiplied by 10 minus x. Now the boundary conditions are given: y0 equals to 0 and y10 equals to 0. That means at x equals to 0, y equals to 0, and at x equals to 10, so y equals to 0. Now we need to find the value of the parameter a1, which is there in the trial function, by the following methods. Now what are those methods? We need to use the point collocation, then subdomain collocation, then least square method, and Galerkin's method. So these are the equation given, and some trial function it is also given here, and corresponding to that condition, two different boundary conditions are given. Now 4 different methods are given by which we need to find the value of the parameter a1, which is there in the trial function. So first we need to find the value of d2 by dx2 from the trial function. Now in this trial function it is given 10a1x minus a1x square. So that means dy dx, it will be 10a1 minus 2a1x. So this is the value of dy dx. Now if we do the second order differentiation, so that means for the first part in the right hand side 10a1, it is constant and it will be 0 with respect to x, and the second part, which was minus 2a1x, now here if we do the differentiation with respect to x, then it means it will be only minus 2a1. Okay, so that means we are getting that the value of d2 by dx2, it is only minus 2a1. So that means what? The residual here, capital R, this is equals to minus 2a1 plus 50. Now if we need to use the first method, that is the point collocation, then the residual capital R, this will be equals to 0. So that means minus 2a1 plus 50, this is equals to 0. So that means what? 2a1, this is equals to 50, and we suggest that a1, this is equals to 25. So this is the value of the parameter a1 using the point collocation method. So that means the trial function, it will be y equals to 25x into 10 minus x, which we have solved using the point collocations method. Next, we need to find the solution of the parameter a1 using the subdomain collocation. Now in this method of subdomain collocation, the formula is integration 0 to 10 r dx, this is equals to 0. Earlier in the point collocation method, it was actually only capital R equals to 0. Now here integration 0 to 10 capital R dx equals to 0. Now here in this equation we need to put the value of capital R, that is the residual. So the value we can see in the first part of this numerical, that is equation number 2. Here the value of capital R is written, which is actually minus 2a1 plus 50. So that means if we put this value here, we are getting integration 0 to 10 minus 2a1 plus 50 dx, this is equals to 0. So that means for integration 0 to 10 minus 2a1 dx plus 50 dx, this is equals to 0. Now if we do the integration within the limit 0 to 10, so first we are getting minus 2a1 dx integration. Its integration is minus 2a1x plus 50 dx, means it will be plus 50x, and the limit of this mathematical representation, it will be from 0 to 10. So that means if we need to put the value of x as 10, from that we need to subtract that part where we will put the value of x equals to 0. So that means that part will be totally 0, and we are left with the first part only, where we need to enter the value of x equals to 0. So that means putting the value of x equals to 0, we are getting minus 20 a1, this is equals to minus 500. So that means a1, this is equals to 25. So that means using the subdomain collocation method, that means integration 0 to 10 r dx equals to 0, using this relation also we are getting the same value of the parameter a1, which is 25. So this is the methodical difference in between the point and subdomain collocation. In the point collocation, capital R equals to 0, and in case of the subdomain collocation, integration 0 to 10 with the limit that is given here, integration 0 to 10 r dx, this is equals to 0. Next we need to use the least square method, by which we need to find the value of a1. Now in the earlier subdomain collocation method, we have seen the method is integration 0 to 10 r dx equals to 0, but in case of this least square method, that I equals to integration 0 to 10 r square dx. This is the difference in between the least square method, then subdomain collocation, and point collocation. In case of least square method, it will be integration 0 to 10 r square dx. Now it can also be written as del I del a1 integration 0 to 10 r del r del a1 dx. Now as we know the value of r, this is equals to minus 2a1 plus 50. So that means del r del a1, with respect to a1 we are doing the differentiation, so it will be only minus 2, because the last part of this right hand side, this is a constant which is 50, so the differentiation it will be 0. So that means del r del a1, this is equals to minus 2. Now we need to put the value of this capital R and del r del a1 in the equation number 5. So we are getting the del I del a1, this is equals to integration 0 to 10 minus 2a1 plus 50 multiplied by minus 2 dx. Now in this least square method, this del I del a1, it should be equals to 0. So that means integration 0 to 10 minus 2a1 plus 50 multiplied by minus 2 dx, this is equals to 0. If we do the integration and of this equation, then after several steps we will get the value of a1, this is equals to 25. So that means using the least square method also we are getting the same value of the parameter a1, which is 25. So the trial function here, it is y equals to 25x into 10 minus x. And last, we need to use the Galerkin's method. Now in this method, the trial function itself considered as the weighting function wy. Now the formulation relation in this Galerkin's method, it is actually integration 0 to 10 wy r dx. This is equals to 0. Now the trial function y, it is given in this numerical, so that is actually the w, so which is a1x into 10 minus x. If we put the value of w, which is the trial function, and the value of r in this Galerkin's method relation, then we need to do some calculation, first some multiplication, and after that we need to do the integration within the limit 0 to 10. If we do this part, then after several steps we will get the value of a1. This is coming as 25. So that means the trial function will be y equals to 25x into 10 minus x. So that means what? Using all the different four methods, that is point collocation, subdomain collocation, least square method, and Galerkin method. So using all these four different methods, we are getting the value of a1. It is same, and it is 25 for all these cases. Okay, so these are the method, weighted residual method and the Galerkin method, which we have discussed today, and we have seen different numericals, how to solve those numericals using the weighted residual method, then point collocation, subdomain collocation, and Galerkin's method. So we need to remember those formulas, like in case of point collocation it will be r equals to 0, then in case of subdomain collocation it is integration 0 to 10 r equals to 0, then in case of this least square method it is integration 0 to 10 r square dx equals to 0, and in case of the Galerkin's method it is integration 0 to 10 wy r dx equals to 0. So all these relation for the four different methods we need to remember to solve such numericals based on the weighted residual method concept. So this is the end for this lecture.